So I'm glad to be here with you tonight. It's great. It's fun to chat with all you guys tonight. The last 10 days or so of January, I was at Quartzsite at the Quartz Fest camp out. There were about, I don't know, 500 of us there camping out there in the desert, and and we had a really good time. It's all dry camping, and when I'm out there, I have six or seven friends that I camp with. And in some cases, it's the only time that I see them each year is when we go out there. But we set up our RVs in kind of a circle, much like the settlers crossing the Great Plains might have done with their Conestoga wagons. But as we did that, we had a number of, portable operations as we were working in an RV. So for example, I had a 17 and a half foot extendable pole in front of my RV. I was working an FT 891 and I had about a 20 amp hour battery that I was working. But of course, I had the ability to use my RV's generator and that kind of thing to recharge that battery. The guy next to me had a couple of strands of home built DX Commander up in the air, about 25 or 30 feet. And his FT, or I'm sorry, his ICOM 7300, and he was making contacts all over across the campground or the camp site that we had. One of the other guys had a end-fed half wave, and I don't know any of you know Randy K7AGE. He was camping with us, and he had a big mast on the back of his trailer and a non-resident wire that he tunes using, I think, an ICOM 5100. I'm not sure. But with that, I was able to do some FT8. I got Samoa and Hawaii and Tennessee and all over with just that portable operation, and doing that out in the desert's always kind of fun, and I bring that up just to show that the we had different setups. Mike had 100 amp hour lipo lithium polymer or LiFePO 4 battery. Randy, he went crazy this year. He had like 200 amp LiFePO 4s, a big power solar generator, and about 4 sets of solar panels out there to collect power. But that just goes to the point that, if you'd like to work portable, whether it's, putting a small radio in a backpack to take to a soda, doing POTA where either you walk in or do what I call tailgate soda or POTA, I mean, or perhaps a picnic table POTA where you just have a short distance to walk to your place where you're going to operate from. Having an idea of the amount of battery that you need, the amount of power that you're going to need for your outing to be successful is one of the things that's kind of important. And that's kind of what we're going to spend a little bit of time talking about tonight. See if I can get my slide to change here. So the question is, what's better? You maybe have gotten input from folks when you're talking about batteries, and you say, what should I do? And some people will say that the best alternative is to get the biggest and that will fit in your coach or in your car or in your backpack, or the most that you can afford. And that's one of the things that you should do. Other people look at it a little differently, and they say, pick the size that meets the need. And so have an idea of what it is you want to accomplish, and then find a battery that will provide the power to allow you to accomplish that particular outcome. Excuse me. And when we get to the end of this, hopefully we'll be able to answer those two questions. And so by way of an overview, we're really going to talk about some basic terms, not going to spend much time there because you know all these terms. There's nothing magical about them. But I only bring them up because these are the terms that are going to kind of form the boundary of what we'll be talking about tonight. We'll talk a little bit about batteries and some of the things that you're going to want to consider with these batteries. We want to talk about power output versus power use, and how mixing those two terms up can really have a negative effect on the computation that you use. And then the heart of the message will be about figuring out what that capacity should be for what it is you want to do. And then we'll answer that intro question that we just talked about. So in terms of terms, of course, a lot of what we're going to be trying to compute is going to be based on Ohm's law, which is just the relationship between amps and volts and resistance and power. And those are going to form kind of the basic understanding of what it is we're going to be computing. And then we have radio power output. This normally is expressed in watts, and it's what's measured coming out of the back of the radio into your coax. So it's going to be the wattage, the 20 watts, the 100 watts, whatever it is that you've got your radio set. That's we're going to refer to as the radio's power output. The power consumption, on the other hand, is normally expressed in amps, and that's the power going into the radio. And that power includes what I call the radio's overhead. And so this is something that we're going to want to understand as we make an accurate computation of what it is we want to be able to do. I've got two duty cycle definitions here. They're slightly different. This duty cycle is how long you're transmitting versus how often or how long you're not. And that's while the press to test or press to talk button is pushed. And that's based on the mode. And again, you're familiar with this, an AM carrier is going to be 100% single sideband, typically is around 20%. FT8 in other digital modes are 100% duty cycles. That's what I'm talking about when we use the duty cycle here. The operator duty cycle is you, and that is how much time do you spend transmitting versus how much time you spend listening. And so that number is going to change. So if you're out on a POTA expedition, the time spent transmitting versus listening is probably going to be closer together than if you're just strolling through the band, single sideband, seeing if you can pick up a CQ or occasionally calling CQ yourself. But that would be something you would want to decide for the particular mission you're on, whether you're going camping and just enjoying the outdoors and play radio a little bit in the afternoon, or if you have a purpose to hit that, activate that park, for example. The other term that we'll refer to is battery chemistry. And that, again, we've got basically two choices, the PB or the lead acid battery plus the much newer, and as I think we'll see here as we go through this, a much more versatile battery chemistry of LiFePO4. And that's the chemical description is, Li for lithium, Fe for iron, and PO4 for phosphate. So lithium iron phosphate would be the other battery chemistry we'll be considering tonight. Also related to battery is the depth of discharge. In other words, how low can you go? You're thinking of doing the old limbo at a party or something. And the batteries have different depths of discharges, and that's going to play into the formula as we see going forward here. So here are our Ohm's law circles. Again, you're familiar with these, volts, current, the resistance. If you know two of the variables, you can compute the third. And then on the other side, the pie chart, the power, current, and voltage. And if you know two of those, you can compute the watts. And if you're missing one of them, you can use the other one over here to compute that. So those are going to be important relationships that are going to be part of these computations. Now, I pulled this table somewhere off the internet. I don't remember if it was Wikipedia or somewhere else, but this one refers to duty cycle, and it's that technical definition of duty cycle. And so you can see here that a conversational single sideband, as a rule, is probably got about a 20% duty cycle, whereas opposed to over here, we've got, slow scan TV, we've got voice FM, digital FM, just a carrier alone. Those are all 100% duty cycles, and that's going to make a difference in terms of how fast we burn through our batteries. And so when we look at the computational tool that we'll look at here in a little bit, you'll see where the builder of that tool has given you some ideas of what you should be considering and have entered then into the boxes in the tool that provides you with the estimate of what the power is that you need. So let's talk batteries for a while. Here's our old favorite, the lead acid battery. There are a couple of things we want to pay attention to. One is the discharge curve of that battery, and that is how it expends its energy as you use it. The discharge limit, and that is how low you should take the battery. And I think with these lead acid batteries, most people would say that you want to take them down no more than about 50%. I have two of these in my RV. Each of them is an 84 amp hour battery to fit under the step there in my Class C motorhome. And so between the two of them, I've got 84 because I normally don't take them down below 50% to avoid things happening to the lead plates that make up the battery. And then those lead plates feed into the third characteristic there, and that's weight. And these, of course, are heavy, as you know, if you've changed the battery in your car or even a smaller battery in your lawnmower, they're quite heavy. So in this chart, we're going to look at a lead acid battery. And on the blue line, and these are notional, it's not a test I ran, but it's just kind of to give you the idea of how these things work. And here you can see that a lead acid battery discharges fairly evenly over time, with the voltage dropping as the time goes down. Now, the other thing that we sometimes forget to think about with one of these is that there's a low voltage cutoff for your radio. So on my Yaesu radios, I think the low voltage or the desired voltage is like 13.2 volts plus or minus 15%, which means 15% of that is about, on the negative side, is about 11.72 or 73 volts. And so where this line crosses the discharge line, that's the end of my battery for all practical purposes. Now, in my RV over here, could I turn on the lights in the coach and do that kind of stuff? Absolutely, because those little LEDs are not voltage dependent as much as my radio is. But here's where I'm going to lose my battery on my radio because I've crossed the low voltage cutoff for that radio. So all of this represents little electrons lying in wait in that battery that I can't use, that I can't get to. And so that's something that we need to keep in mind as we make a choice on battery chemistry moving forward. Now, in the LiFePO4 batteries, we've got those same three considerations that we need to think about: the discharge curve, the limit, and the weight. And so we're back to this very same chart, except you'll notice that I've moved the low voltage cutoff over here, and that represents where this curve is crossed. And so again, it's about 11.72 or 73, but you can see that's a lot of more energy available to me in my radio before my radio is going to turn off. Now, the curve for a LiPo is generally starts at about 14, 14.4, and then goes down very quickly. And then it levels off at about 13.2, 13.3, something like that. And it goes and it goes and it goes and it goes all the way to where it doesn't. And then it falls off quite rapidly. Now, people will talk about, well, you shouldn't run the battery to 100% discharge. Some will say, treat the battery kindly and maybe only go to 80% or 90%. But as you can see in this chart, when you get to the end, there's not a lot of time involved between getting to 90% and getting to 100% because the curve is so steep right there. And so this for all practical purposes, 100% discharge is not that big a deal. If you want to baby your battery a little bit, go ahead, that's fine. But it has inside a battery management circuit. It may be a large board. If it's a big 12 volt, 100 amp hour battery, it may be something more small. If it's a 4 or 6 amp hour battery, but it's reading the voltage and it's going to turn the battery off because these LiPo cells generally are going to be damaged if they get below about 3 to 3.2 volts. And so when the low voltage cutoff of your battery is triggered, there's still voltage there. And so it's not like that lead acid battery that'll just take it down to nothing. The computer chip there in the battery is going to stop it before it hurts itself. And the more expensive the battery and the bigger the battery, it's going to have things like self-heating and all kinds of other magic. But this isn't about battery, a presentation about battery. It's about computing capacity. So we'll just leave it at that. So we see then we've got a discharge limit, and then the big thing is going to be the weight. And I've got another slide here. And so I went to Amazon and I said, well, what's a 50 amp hour LiFePO 4 weigh? And I looked at several of them, and they were all, in the neighborhood of 18 to 20 pounds. Now, that's not insignificant, but, it's not too bad for 50 amp hours. Again, thinking 100% of discharge. Whereas with our lead acid battery, we've got another problem, and that's at 50% level. And so 50 amp hours of available power with a lead acid battery meant that I'm buying a 100 amp hour battery, and those on Amazon were about 60 pounds, which makes probably a little more than you'd want to put in your backpack to carry on a hike. And so the lead acid has got that drawback of weight that you need to be mindful of. Now, power output versus power use. And so we defined those already, but just with a quick reminder, the power output is measured in watts, and that's the RF that's leaving the radio, going out through the coax toward the antenna. The power use, on the other hand, is measured in amps, and it's the measure of all the radio's functions. So it's not only the energy used to output power output, but it's the stuff that keeps the light on the radio. It keeps all the other circuits energized, and all of the multitude of things happening inside the radio. And so we want to figure out how much power are we using? That's going to be the big challenge to compute our battery capacity. So how are we going to figure it out? Well, one way, of course, would be to measure it. And in a lot of cases, if you're using, the budget class or intermediate class radios, that might be the only way you have. I know with some of the radios I have, little mobile rigs, the spec sheets in them don't tell me what the power usage is. Whereas with my Yaesu radios, for example, and an ICOM radio, back in the spec sheets, it'll tell you what the radio is using. So let's look at the measuring thing first and figure out, what that's going to look like. So this is just a little watt meter. Now I fly RC airplanes as another hobby, and I use this to test my electric airplanes. And that's really important to do. And so with an electric airplane, there are a couple of things that we need to be mindful of. One of them is the voltage, in other words, the size of the battery, the electronic speed control that tells the motor how fast to go, has an amp limit. And so we want to make sure that we stay well below that. And then when we start messing with things like the pitch of the prop or the size of the prop, that's the resistance coefficient. And so it's not unusual to see somebody out at the flying field have an airplane that's running pretty close to the limits. They have a rough landing and they replace the prop with something bigger. And the next time they fly, They see what I call the magic smoke coming out of the airplane because the ESC has burned up. And that often means that power to the receiver is also burned up, which means, yeah, they're going to be making the walk of shame out to the airplane to retrieve it from the crash. And so being able to measure in that situation is what these little guys are often used for. In this case, I've got it connected to a mini mobile receiver, and the battery is on this side, the receiver is on this side, and with the receiver just idling, nothing being received and but turned on, you can see it's pulling about 1.9 amps. The battery shows 13.88, and it's got about 2.6 watts, and that's just the Ohm's law being converted there that we saw those diagrams of. But when I set the radio to 5-watt output and press to talk, then I can see that my amps go up quite a bit, almost 10 times. The battery sags a little bit, and the wattage used during that transmission is gone up to 23. And so this amp number becomes important in our computation because that's our transmitter amps. Now, take this into a 100-watt radio. You can see these numbers are all going to be quite a bit bigger. Now, in this example, I've got the same little radio, but this time I set the power on the radio to its high setting. And you can see here that the amperage went up to 3.83 amps versus the 0.19 over here. 50 watts going to power that entire radio, not just the power output, but the whole radio. And then the battery sagged a little bit more down to 13.2 volts while the push to talk button was pressed. And so this gives us a good idea of what we're going to need for our computation using a smaller radio. The same thing would work with a big radio. The capacity of these little meters is surprisingly large. And so you can measure for yourself if the radio spec sheet doesn't show you what it's using. Speaking of the spec sheets, this is the couple of Yaesu radios. And so you can see down here, it has this label of current consumption. And so when it's receiving, it's 0.5, the FTM 400. In the 2-meter, it transmits at full power, 50 watts, at 11 amps and 12 watts in the 70 centimeter band. My FT710, 100-watt radio, an HF, also has those same numbers. And so without a signal, it's about 1.8. And if it's receiving something, it's about 2.2. I suspect some of that's the speaker being powered and so forth. But then when you transmit with 100 watts of power, the radio is consuming 21 amps to produce that 100 watts of power. And so this makes it really easy in our computation because it's just printed out there. Now, in most cases, I'm going to use that 100-watt number just simply because it gives a reserve. When I was out doing FT8 at Quartzsite, my radio was set to like 30 watts. So I'm not running 100 watts for that. But to the extent that I run a lower power setting, I can expect this amperage number to be lower. And if I'm really curious, I put the meter on it and measure and see what I'm pulling through the radio with that lower power setting. So the important point to remember here then is that the power output divided by voltage does not equal power use because it doesn't account for the radio's overhead. It doesn't account for all those things that generate heat, the inefficient final amplifiers, the lights in the radio, lights in the microphone, all the stuff that happens in the radio that does not result in RF leaving out of the radio. And so I've made this mistake myself when I was just in a hurry making the computation, and the computation just didn't make any sense to me. And I says, "Oh, dummy, you're not using the right output number there." So how do we figure this out then? Well, there's basically 3 ways that I've come up with. Excuse me. One of them is just a rule of thumb. And as with all rules of thumb, it's just a pretty broad estimate and not particularly accurate across a wide range. Although in some cases, as we'll see in my examples, it does come pretty doggone close. The other way is to do manual computations, and we'll go through a couple of examples there. And then I'll point out this online calculator that I find really handy because it allows you to make changes and then just instantly have all those computations made by the computer in the background and just display the output to you as you try to make some decisions about either which battery you're going to take with you or which battery you maybe want to buy to add to your collection. So the rule of thumb is this, and that is use a battery with twice the amp hour ratings of amps your radio draws when transmitting. And, consider a fairly conservative duty cycle when you do that. And so with my 710 with 21 amps when I'm transmitting at 100 watts, that would be a 42 amp hour capacity or a 50 amp hour battery. Now, I know a lot of you are thinking to yourself, man, that is not even close, because if I'm using low power and that kind of thing, that 50 amp hour battery is going to be just a lot of overhead. And you're absolutely right. That's the broad part of the estimate of a rule of thumb. But as we'll see in a minute, there's going to be some situations where that rule of thumb really is going to be pretty close. And so we'll look at that here in just a second. The other thing we can do is we can compute the battery capacity using a formula. And that formula is here on the screen right now. It starts with and the terms are defined down here. So the percent of transmitting, the transmit amps, that would be that 20 coming from that Yaesu spec sheet. The duty cycle, the percent of receive, again, depending on what you're doing, 80%, maybe 60-40 if it's a POTA, 50-50 if you're pretty aggressive with FT8. This can change. And so this is a variable you get to input. The receive amps, and again, with my little Yaesus, about 2 amps in receive. The desired hours, that's over here, and that's how long do you anticipate being there. So you're going to spend the afternoon doing a POTA, and you think you can get it done in 4 hours. That would be the desired hours for this computation. And then all that then equals the required amp hours. So let's use a low power example to start with. So in this case, we're going to do single sideband. We're going to go out and do some POTA. We've got an 80-20 transmit to receive for our computation. We're using a 100-watt radio. That radio is my FT710, so it's got a 20 amp power consumption when I'm transmitting, 2 watts or 2 amps when I'm not. I'm going to be using single sideband, so the duty cycle is going to be 20%, and I hope to be out there for 3 to 4 hours, and so that's the desired operating time. So when I put these variables into the formula, this is what I get, and rather than go through each of these steps in the equation, you can see I'm just boiling this stuff down to combine these various parentheses, multiplying it by 4. When I get down nearly to the end, I've got 0.8 plus 1.6. That's my transmit versus my receive, and I'm multiplying that by 4, and I'm getting 9.6 amp hours using single sideband. So in this example, that rule of thumb was like way off, right? Well, 9.86 versus 42 amp hours. And so at this end of the range, the rule of thumb isn't particularly good. But now let's take a look at another example and see how that might change. In example 2, let's say we're going to do that same go camping and we're not doing anything special, but we want to play radio out on the picnic table in the woods. And so we're going to do some FT8, so our 50-50 transmit to receive ratio. We're going to use 100 watt. Yeah, normally we wouldn't use that much power for FT8, but for our example, we'll use that. 20 amp power consumption on transmit. FT8 is a digital mode, so it's going to be using 100% duty cycle. And again, we want to be able to play radio on this particular camp out for at least 4 hours. And so that's the input going in. So when we go through this, we've got kind of that same formula, and we've got 50 times 20 and then 50 times 2. It boils down neat and tidy. We end up with 11 amps per hour with that set of constraints that we've defined up here. And we want it to last for 4 hours, so that gives us 44 amp hours. And so in this case, our rule of thumb was really close. It was 42. This one's 44. And so we would, for 4 hours, want to have a 50 amp hour battery with us or something in excess of 50 amps. And so at the higher end of the computations, the rule of thumb becomes a little more accurate and something to keep in mind, depending on how exact you like to be when you do these things. So the other thing that we're going to want to do then is examine an online tool. And this will allow us to do a lot of what ifs, which make it really kind of fun. This one is available here at this link. It's in a QRP type page. It's a tool from W1PNS. And it runs and it gives you this kind of a display, and the computer does all that arithmetic for you. And it uses the terms that we've previously defined. And so let's take a expanded view at this display and see what we got. So this is our single sideband example. So we've got desired hours is 4. We're using single sideband, and that is the 20%. Duty cycle is up here. They've defined some typical duty cycles up here, which match the drop-down box here. We've got the operator duty cycle. That's the amount of time I'm going to spend as the operator talking versus listening. So that's going to be 20%. And then my radio's got 2 amps on listen and 20 amps on transmit. And this battery I'm going to take down to 100%. And if I was using a lead acid battery, I'd put 50 in this number because that's going to affect the number of hours here. But since I've got a 20 amp hour battery and I'm going to use all 100 amps, that's what the formula is going to use. And so it tells me that my average current is just under 3 amps. I need 10.88 hours, and 10.88 hours with a 20 amp hour battery will give me 7 hours. And that's very close to that manual computation that we just made. We had 9.6. This comes up as 10.8. And so if we were to put a 10 in here, it would give us just under 4 hours, and the program would give us a little warning that says, oh, you need a bigger battery. But again, if you know what's happening here in the computation, you can say, yeah, that's close enough. I may not use all 4 hours, that kind of thing. So here with this, we see that we got really close to that example where we computed all those variables manually. In this slide, we're going to take a look at the FT8 example that I gave. So again, we've got 4 hours, digital mode, the operator cycle is 50-50, 2 and 20 for the receive and transmit amps. Again, a 50 amp hour battery with 100% discharge level. And we end up then with 11 amps per hour, which is the same as we got with our manual computation, and 44 amp hour capacity, which is exactly the same as what we got with our previous computation as well. And because we said we were going to bring along a 50 amp hour battery, then it tells us we've got 4.5 hours of estimated usable time for this particular portable operation. And so you can see that by using this tool, you can change the values up here. You can give an idea of how many batteries maybe you want to take along. If, like for but 2 weeks ago, the winter field day that was happening with ARRL, you have an idea of um, how you want to provide power for your rig, again, depending upon what it is that you want to do. So let's take a look at these side by side for just a second. And so we can see there with our single sideband example, we went through all these, or this is our FT8 example. We went through all this, 4 hours, 11 amp hours per hour, 44 amp hours. And so that's what we got. And there we go. Same thing over here. And so in this case, at this higher capacity, the two come out the same. With that lower level, there's something different. I don't know exactly what it is, but we are still really close, 9.6 versus 10.8 amps. And we'll know that with that 20 amp hour battery, we would expect 7 hours. We only want 4, so we're good. But that also means that we could probably take perhaps a slightly smaller battery with us, and that would become particularly important if we were having to cart the battery and the radio a long way. So how do you expand your capacity? And of course, the easiest way to do that is with solar panels. And so the example that's on the screen now is a portable solar panel. When it's all folded up, it's like 11 by 14. So it's really pretty small. There are a million kinds, a lot of sizes, a lot of wattages out there. Some of the solar panels have built-in charge controllers, which you're going to need if you're charging your battery. Others of them, you'll have to purchase the connecting wires and the charge controller separately. But using a charge controller with solar panels is a great way to extend the capacity. I mentioned my friend Randy with his Force, I don't know, 400 watts of solar panels set up in front of his trailer. And because it was sunny the entire time we were in Quartzsite, except for the afternoon, maybe one day, he was able to keep completely powered without ever starting a generator, which included running his coffee maker in his camper and that kind of thing. So again, it's not a solar panel lesson, but this is going to be one of the things that you're going to want to invest in or investigate at least if you do a lot of portable operations. So I asked early on, what's better? That's kind of what we started this whole session on. And is it the most that you can fit or afford? Well, that answer is probably yes, if you've got an RV or another vehicle in which you're going to be using these batteries, and so space and weight are not a big deal. If you're doing a POTA from a tailgate or from the back of your SUV in the parking lot of this park, this could be a very good way to do the most you can fit or afford. Or if you don't have far to go, I kind of refer to this as picnic table POTA, where you maybe have 20 or 30 yards to walk to a picnic pavilion, and carrying a larger battery than you need is not a big deal. They're not that heavy, especially the LifePo 4. So that would be an answer that would say, yeah, the more you can fit or the most you can afford would be a good answer to answering the question, what's better? On the other hand, how about the size that meets the specific need? Well, if you like to do backpack POTA, where you're walking into the park a long way, or maybe there's a place in the park where there's a trail that crosses through, and so you can get a twofer on your POTA activation, and you don't want to be carrying around more weight than you need to do that. And so sizing the battery to meet the specific need in that case might be exactly what it is that you want to do. When we were in Quartzsite, one of the activities was doing a soda hike up to Guadalupe Peak. And so if you've got, kind of a man-pack radio with the radio and the battery and antenna all shoved into a 40 or a 50-liter backpack that you're going to carry up to the top of the hill, again, not carrying a bunch of battery capacity that you're not going to need, probably that weight and that space could be used for something else, another bottle of water or something like that for your hike. And then obviously, if you're an outdoorsman and a out back kind of backpacker, but you still like to play radio, you could bring one of those little radios like the Zygoos or the ICOM 705s with you, and a small battery, maybe a small portable solar panel that you could set up for a little bit in the morning, or even hang on your backpack while you were hiking between campsites. That would mean that, having a size that meets the need would probably be a better choice. And then, of course, if you're doing some emergency communications and you've got a go bag, and this might mean, a VHF or UHF go bag, having battery there that would allow you to do local communications, or if you want HF communications, in a bag ready to go, charged up, so you have to, if you need it in a hurry, or if you've got the anticipation of a storm or that kind of thing, you could have all that all set up, ready to go, and you're able to deal with having some enhanced communication ability based upon what you anticipate. And because that might mean, leaving in your RV, leaving in your car, might mean a big 100 amp hour battery. It may mean a little 20 amp hour battery. Again, depending on what it is that you're trying to accomplish, these various computations will allow you to be successful in what it is you want to do. And so as we wrap this up, we've got a couple of things that we've looked at. We've looked at, the different battery chemistries, and that's going to be important because of the discharge curve, how much you can discharge them, and then also their weight between the LiFePO4 and the lead acid. We looked at a couple of ways to do some computations. We looked at our rule of thumb, we looked at our manual computations, and we looked at the online aid that allows us to get pretty exact to figure out what we want to do. And so that's pretty much what I've got for you. I'm not claiming to be an expert on all of this stuff. We can deal with some questions if you like, or better yet, some personal experiences that you may want to add to the group in ways that you've addressed this problem in your own portable operations. So I think I'm done.
Oops, let's get this out here. Questions, anybody?
In the chat, someone wants to say they need an ambient temperature variable somewhere.
I'm not sure I understood that.
They need to have, in one of the formulas, they need to have an ambient temperature variable.
Perhaps lithium batteries don't do well in the cold, and that's why some of them have those self-heating elements. I know I was a military pilot for many years, and in the survival training we had, one of the first things we did is we took our survival radio out of our parachute if we were to had to, abandon the airplane, and in cold weather, put it between our flight suit and our jacket to keep it warm. And so that's certainly true. And those weren't lithium batteries. Those were the probably nickel metal hydrides. So yes, in fact, if you're working in cold weather, that will have a negative impact. So that's a good point.
Anybody else? I guess it helped if I turned my camera on. Anybody else out there?
Well, anybody else doing it? What have you decided to do? Do you have some batteries that you use, and in what circumstances do you use them? I'd be real interested in that if that's something that, those of you who are part of this group happen to do.
Puerto Rico never uses any batteries, do they?
I know I was using with the Yaesu FTDX10, a 30 amp hour Bioenno battery, and run an FT8 nonstop. I could get close to 4.5 hours out of it, running at about 85 watts
Okay.
in temperatures close to, I want to say 85 to 90 degree Fahrenheit, in the Northeast here, New Jersey.
Oh, very good.
I can tell you if you're interested. I'm building a MCOM's trailer for my club, the Marine Amateur Radio Club, and in that we have a couple of 200-watt solar panels running a couple of 100-watt LiPo batteries, and we'll be powering up, obviously, the LED lighting in the trailer, the 3 computers that are little 12-volt computers and monitors, and we'll be running 2 or 3 radios at the same time. And so I'm crossing my finger that we'll have enough capacity. The beauty of the system is we're able to add more 100 amp hour batteries as we need it. So we're starting off with 200, and so time will tell what will really be required.
Yeah, the 100 amp hour batteries have really gone down in price quite a bit. We don't know what tariffs are going to do, but a reasonable 100 amp hour battery for under $200 is not unusual. And then the other thing you've got is adding solar panels. Add the wattage. If you're working in sunny skies most of the time, you can refill them as you're using them. So that sounds like a really fun project.
I was wondering what's the specific need for the charge controller itself rather than just hooking up directly to the solar panel. What are the implications of that?
We're starting to get out of my wheelhouse a little bit, but I think it is that the battery expects about 14 volts going in, and solar panels can output anywhere from 12 to 48. And so the charge controller is what takes whatever wattage you're getting and whatever voltage the solar panel is producing and puts it into a form that LiFePO 4 will accept without damage.
Okay, so like an uninterrupted power supply would do to your computer equipment or something at home, condition the line so that it's not spiking up and down.
I think that's a fairly good analogy.
And
The
also
charge controller is a regulated device.
also to prevent overcharging the battery.
That too, yes.
The other thing you want to be careful about with solar controllers is hash and RFI. And there's a ham that builds a solar controller. It's DIY Solar. That's specifically well designed, especially if you're going to do HF. And I've had good luck with that one.
Very cool.
And remember that the charge controller needs to be purchased according to the battery chemistry you are using, because seal lead acid battery charger won't charge LiPo 4. There are some in the market that can be switched from one battery chemistry to the other, but if you have a old style charger designed for seal lead acid, it won't be a good choice for LiPo 4.
Yeah, the charge controller is a whole other presentation there, because you need to decide whether or not you need a MPPT charge controller or a PWM. I mean, there's a lot of things to discuss about that. But
The other point important for ham radio use is that many, or probably all, of the cheap charge controllers that you can get from Amazon or eBay are quite noisy. So they will add a lot of RF hash to your receiver. We have to look for specific charge controllers designed for communications equipment to ensure they won't introduce a lot of noise. Like, for example, if you do a search, you will see that the Jenison has some models that are very quiet, as well as the ones sold by Bodypole. The one from Bodypole is very it's a very good one, a very good option for ham radio use. It practically is silent. There's no noise introduced to the radio receiver.
Very good point.
Ferrites are your friends.
Yes.
Ferrites are used when you have a bad design. If you have a good design, you don't need ferrites.
Well, that unless you're really hungry, because I had a couple ferrites for
I've
breakfast.
seen
just in
I've
case.
seen ham operators connecting an inverter to a battery and then a power supply to the inverter to power a 100-watt radio. Forget about the inverter. Hook up the radio direct to the battery. You are going to introduce a lot of noise, and in the case of a modified sine wave inverter, you are going to kill your power supply eventually.
Just talking about the trailer, that's why everything is designed to run 12 volts. There's nothing in the trailer that requires 120 volts. So I do not have an inverter. I do have a shore power in case I want to charge the batteries using a shore power. So I do carry a generator just in case, when all else fails. I think 2 is 1 and 1 is none. So having multiple ways of charging your battery is a good thing. But using the generator as a last ditch effort, that's why I plan on using the proper amount of amperage in the batteries themselves. But that's just me.
Sounds like some good practices there. Sounds like you've been there, done that, is what it sounds like.
Many times.
Anybody else? I don't see hands up. Barry, how we doing in chat? Barry. Did he leave us? Maybe he left us. Huh. Well, okay, he must have left us.
I have one more thing to say. Thank you, Jim, for your service. I appreciate your dedication.
Oh, thank you.
And next time you see Randy, tell him hi from me.
Okay, will do.
Anybody else? Anything?
I'll mention I bought a 50 amp hour lithium ferrous phosphate a couple years ago, and on one particular trip I used it for I think 4 successive parks on the air activations that each lasted 2 to 3 hours without recharging it, and that was running a ICOM 7300 at full 100 watts. So it'll give you some nice capacity. I chose the 50 amp hour size because that was the biggest capacity that I felt was pretty portable. But it's all a personal decision as to, what fits your budget, what fits the space and weight that you want.
Good advice. Good advice. Okay, back to you there, Jim. Got anything more?
No, I think that's it. I appreciate your attention tonight, and I value the conversation. Picked up some good pointers from you all. Thank you.
Yeah, I got a quick curiosity question. What did you fly in the military?
My first assignment out of pilot training was in B-52s, and then I left the Buff and spent a good chunk of my career flying T-37s as an instructor pilot. So I have a lot of time in the Tweet, and I retired with just a little bit more than 20 years.
Oh, wow. Well, sounds like you had a good career there. Sounds like something that lots of memories, and you enjoyed every bit of it.
Well, most of it. I like to joke with people that when it was time for my midlife crisis, I didn't need to chase women or buy a fast car. I could just make a phone call and go strap on a jet and go fly. And so Uncle Sam paid for it.
A lot to that. A lot to that. Okay, let's do another round here. Anybody else got any questions, comments? Want to share anything?
Just a quick comment, if you don't mind, Dan. Just wanted to thank Jim for his evening thing here. We really enjoyed it. I'm sorry I was late. And Dan, you're looking well. I haven't seen you for a long time, and it's good to see you again. Hope everything's going well for you. Thank you.
Brett, it's been forever since I've seen you. I hope you've been okay. I wondered about you. I like thumbs up. I like thumbs up. Okay. If there's nothing else, I'm going to pull the plug and see you all tomorrow, hopefully.
7-3 to everybody. Thank you for coming.
There you are, Barry. I thought I lost you.
Oh, I was here. I've been listening. I've been watching the chat.
Okay. Okay, well, 73s, everyone. Have a good one.